Hello, we are Team Dr. Strategy Plus and I'm Jionu with Subin Kim and Igor Alentev. We are going to discuss about our progress. To quickly recap our proposal, our project is based on the paper Dr. Strategy. The central innovation of Dr. Strategy lies in its approach to goal-conditioned reinforcement learning. Unlike conventional methods, this system starts completely from scratch, relying solely on pixel-based images as input. By starting from scratch, the model explores and learns its environment autonomously without relying on any prior information or pre-trained knowledge. This characteristic of Dr. Strategy, learning directly from raw data and generalizing across a wide array of goals, makes it a promising framework for advancing the field of AI in open-ended problem-solving contexts. Built on top of Lexa, Dr. Strategy adds a divide and conquer approach leveraging the structures of latent landmarks. These innovations enhance the efficiency of dreaming in model-based reinforcement learning and improves both the exploration capabilities and the goal achievement quality of a generalist agent. For example, consider the task of reaching a destination. Using Dr. Strategy, the agent might first ride a train to a key landmark and then take a taxi to navigate the finer details of the journey. This approach is far more efficient than attempting to drive the entire route by car from the beginning. In this analogy, relying solely on a car and memorizing multiple routes at once mirrors the limitations of Lexa. We use this strategy to divide state space into clusters, focusing our evaluations on the cluster centers. This allows us to efficiently compute essential metrics such as exploration potential and the distance to the goal, without needing to analyze every individual state. Dr. Strategy employs a focused sampling approach for efficient learning. During exploration, it evaluates only cluster centers and begins exploration from the landmark with the highest exploration potential. During testing, it identifies the nearest landmark to the goal, uses the highway policy to reach the landmark, and then the achiever to navigate to the goal. This simplifies training. The highway policy learns only a finite set of cluster centers, while the achiever focuses on nearby destinations. All components, highway policy, explorer, and achiever, are trained using imagination rollouts on a shared world model.
The original paper presents an intriguing concept of training a highway policy to reach a G landmark, but it does not guarantee the optimality of the resulting path. To address this, we propose introducing a hierarchical structure that decomposes the task into subtasks, leading to better overall performance. By enabling the combination and the recombination of multiple skills, this approach could facilitate solving a variety of tasks in a more generalizable way. For example, breaking the task into sub-goals creates a composable structure that enables us to tackle a variety of tasks within the environment. This approach also provides more explicit control over the algorithm, allowing for more optimal solutions rather than depending on end-to-end approach. Additionally, chaining not only facilitates the decomposition of the main goal into simpler subgoals, but also supports recursive decomposition, further enhancing the efficiency of the solution. The task can be broken down into two main components, defining optimality and then finding a path that satisfies this definition. To define optimality, we first need to assign weights to the edges between landmarks. These subgoals will then be connected to form an optimal path. There are several ways to define the weights. For instance, we could take a more practical approach and use real-world complexity to assess task feasibility. When it comes to path planning, we can have a variety of algorithmic options, including deterministic, heuristic, and stochastic approaches. The choice of algorithm largely depends on the weight function, so these two aspects must be considered together. Until now, we explained the idea of our baseline and the improvements we plan on top of it. We will introduce the replication and the improvement results. Doctor Strategy works upon three different environments. First is Mini World, where the agent explores 9 or 25 rooms in 2D POMDP setting. Second is Memory Maze, where there are 7 by 7 and 15 by 15 size maps. Here, the agent is given an egocentric view, which increases the complexity since direction is also important. Lastly, we also work upon RoboKitchen, which is given a top-down view, and the robot arm tries to solve tasks such as grabbing a kettle or opening the cabinet door. We decided to work primarily with Mini World, where it is less complex and good for empirical evaluation through visualization. We were able to replicate upon all three environments and have also visualized trajectory and skills. The leftmost figure shows the agent visualized as a green square, moving between rooms to achieve two different goals. The POMDP view in the right shows the pixel-based input given to the agent. The left figures show the visualization of skills. The red dots show the estimated position of skills in the top-down view of the map from the Mini World and Memory Maze. We have pre-trained models to check the success rate and also exploited them during our implementation for improvement.
The models are so large that it takes days to run even smallest environments. As a result, we decided to implement the improvements in the post-train phase to avoid retraining. Moreover, the architecture of original model is very complex and difficult to extend. Hence, we derived modular structure. This structure will allow us to substitute different distance and pathfinding functions and get the results straight away. The overview of our modular structure is represented on the following diagram. For instance, we organized the ways of calculating the distance into 4 different approaches, which we will explain later. After calculating the weights and constructing the graph, we can use this information to find the optimal path, chaining the landmarks leading to the goal. Our candidate algorithms for such pathfinding are Dijkstra and A-star. Data then we evaluate and visualize the results in comparison with the baseline model, as well as various approaches. For now, we were able to implement 2 main algorithms for calculating the distances between the nodes. The algorithm itself calculates integer number of times it performs imagination step to converge from source node to the target node. On RSSM layer, we used MSE loss function as a metric for convergence, while on the embedding layer we used TDP, which was trained alongside the original model. The figures on the slide represent TDP on embedding layer, as it is a more robust solution. First figure shows the paths generated by our model. The second figure shows how nodes relate to each other with our distance function. It shows k nearest neighbors with respect to calculated distances. From animation, it can be seen how algorithm starts connecting disjoint sets when we increase number of nearest neighbors. Even though the distances themselves are not perfect, we can see that they approximate the world good enough. The last figure shows the latent representation architecture of Doctor Strategy. It shows that we tried to calculate the distance upon the 2 representation states, RSSM state and embedding state. We are planning to discuss the effectiveness of calculating the distance with pixel level input in the future.
For our future plans, we will implement other distance functions such as pixel layer TDP and hierarchical VQVAE, and discuss pathfinding functions such as A-star algorithm. Also, we are planning to find evaluation criteria for different distance measures. Lastly, we will evaluate in other environments. These are the timeline that we have finalized, and thank you for listening.